So today we are going to solve Koko eating bananas. This question has been asked in all big tech companies like Google, Amazon, Meta, Microsoft, Oracle, so many companies, right? So this question again, I'm going to show you what is the thought process of using a binary search. I mean, many of you would have tried this question, I am assuming, and have seen that binary search is being used. So basically, the my try I will try to tell you when you can actually use a binary search, right? So directly jump into the question says Coco loves to eat bananas. There are n piles of bananas, n piles of bananas. The ith pile has piles of I banana. That means suppose I have four piles of bananas, one, two, three, four. Here it is two, here it is three, here it is four. So this piles of I is that many bananas, right? So guards have gone and will come back in h hours. So they have gone and they will come back after like h hours. So let's say I have bananas as 2, 4, 3, right? So guard will come after 8 hours. Let's say they will come after 8 hours. So basically, what is the minimum? Okay, I am going ahead. So we'll just read the question. So Coco can decide her bananas per hour, eating speed of k. So it's upon Coco to decide the speed, right? And she will be eating her bananas per hour, right? Each hour she chooses some pile of banana. So at every hour, she will choose which banana she wants to eat, right? If the pile has less than k bananas, If the pile has less than k bananas, she eats all of them instead and will not eat any more during these hours. What it means is that if Coco has decided to eat one pile of banana at a k hour and she has eaten before this hour, so she will not move ahead and eat another pile of banana. She will not move ahead and eat another pile of banana. This is an important constraint given in the question. Coco likes to eat slowly. That means she likes to eat slowly, and she still wants to finish eating all the banana before but she still wants to finish. So you have to return the minimum integer k, that is minimum eating speed, such that she can eat all the bananas within h hours. So at what speed she can eat all the bananas from the pile? Right, at what speed? At what minimum speed actually? At what minimum speed she can eat all the bananas from the pile, right? So again, reading the question, you have n number of piles. Each pile shows how many bananas are there. Coco wants to eat all the bananas, but she has to decide at what speed she wants to do. And that speed, so whatever speed she chooses, she should be able to eat all the bananas before before h hours. Before h hours. H hour is the time when guards will come back. When guards will come back, right? So she wants to eat all the bananas at a speed. You have to find the speed. Basically, you have to find the speed, and this should be the minimum speed. Minimum speed, right? So thinking, going straight to the brute force question, right? So let's say Coco has some piles of bananas available to her, right? So let's say the pile example s 3, 6, 7, 11, 3, 6, 7, and 11, and h is given as 8, and h is given as 8, right? So Coco can eat, or Coco wants to eat all the bananas, but she has to decide at what speed. So I will go from a speed maybe 1 towards n, right? And I'll find a speed at which she can eat all the bananas, right? How do I know that she can eat a banana? How do I know she can eat a banana? Basically, speed is equal to distance upon time, right? I want to find out at what time she eats the total time, which should be less than this. So total time should be less than equal to h, right? So t is equal to d upon s, right? Here distance means bananas, so she wants to cover all bananas, and s is the speed. S is the speed, right? So at each d by s, d by s, d by s, d by s, if I add them, they should be less than equal to h. That is what the question is asking, right? I hope you understand this part, because this part is the one which tells you that you have understood the question or not. So you want to eat all the bananas, but you want to decide at what speed you want to eat. You don't know the speed, right? So you want to find the minimum speed of eating all the bananas, such that the time comes should be less than at 8 hours, right? So speed, as it has been told, is in hours, is in hours, right? So here if I do d by s from 1, there will be different values coming, right? Different values coming. So I've already done it for this. So if you can see this part of the code, right? This, oh my bad. Okay, if you can see this part of the code, I have taken the speed as 1 2 3 4 5 6, right? At one speed, uh since this is d by s, here let's say it's k, s is equal to k, same thing. So the speed will be this. So the total hour calculated is 27. Again, if okay, I am taking the seal value, I'll take the seal value. So basically what seal value is, if seal off, let's say what should I do, 3 by 4, right? So 4 divided by 3 is 0 point something. If it is 0 point something, and if it is seal, it will convert to 1, right? If it is 0 0.2, let's say, it will convert to 1, right? So I'll take all the seal values, right? So now if I do for k equal to 1 or s is equal to 1, so it would be 3 plus 6 plus 7 plus 11, which is 27. Same for k equal to 2, it would be 15, then it would be 10. So whatever, for the total hours k, right? Total hours, which value will be less than or equal to this? So k is equal to 4 is the answer here. So this is the answer here, right? So that's what it is being done in the brute force approach. What we will do is, we will iterate over all the elements, and we will divide all by the speed, and we will keep on adding it, right? If if the hour spent becomes greater than h, anyway I'll break from this for loop, right? And then I will check. If the hour spent is less than, then I'll just, if it is less than or equal to, I'll just return the speed. Otherwise I'll just increment the speed by 1, right? I'll just increment the speed by 1. So here I can say that, okay, I have went through all depending on random speeds, and whatever minimum value, becomes this h, right, hour speed, then it is fine. Otherwise I'll just increment the speed by 1 by 1. Why 1? Because it is given that we have to do per hour, right? That's why 1 hour. So this speed here is the, yeah, the unit is of speed here is hour. Okay, now how do we know that this can be solved with binary search? How can we know that this can be solved with binary search? Okay, so normally what we have learned is, if an input array is sorted and we have to find something in that sorted array, we can normally use binary search, right? This is one of the condition of binary search that most of the people know, that the input array that we are getting should be sorted, right? And if we want to find something and we know the target, then we can find it. That is binary search, right? But there is another observation which helps you to come to the conclusion that a binary search can be used to sort. Okay, so coming back to this example and the solution iteration, you can see that these three gives false, while these three, or any number that is more than 6, will give true, right? So essentially what array is forming, the solution array is forming, is a false false false, then a true 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 true, right? And this is the boundary, where it changes, right? This is the boundary where it changes. So if I say that this, the boundary is n, So all n plus 1 will result in true, right? And all n minus 1 will result in false, right? So that's what I have written here. So if n is the boundary, then all n minus 1 will result in false, and all n plus 1 will result in true. So can you say that this behavior is a monotonic behavior? A monotonic behavior is that behavior which is not random, right? It's not like false, true, false, true, false, true. It's one state and then it's another state. It doesn't change back, right? So if an answer shows a monotonic behavior, if an answer starts to show a monotonic behavior, this is a clear sign of using a binary search. This is a clear sign of using a binary search. Okay, so maybe I'll just say binary search works when input space is sorted or answer space is monotonic, right? Now, with the previous approach, I had a speed of 1 to whatever the minimum value is, right, where the answer comes. But uh, I was incrementing the speed by 1. Can I say that this speed will always be from 1 to the max value of the heap, the max value of the heap? Can I say that? Can I say that? Yes, I can say that, right? So the minimum speed will always be 1, and the maximum speed, because eating faster than this largest pile is useless, right? Because if I'm eating faster than this pile, then it is useless because it will always give you the answer, right? So I have a range now. Which is 1 to the largest pile, right? 1 to the largest pile. So here it could be 1 to 11, right? 1 to 11. Now I have a range. I'll check from the middle. I'll check if I divide this number with all the bananas, is it giving the answer? If it is giving the answer, that means that I should check on the left side. Otherwise I will check on the right side. Again I will do a center. If I divide this and it works always, right, then I will check on the left side. Okay, if I cannot find, then I will check on, otherwise I'll check on the right side. And if it also doesn't work, right, then my right side will be the answer. So that's where the observation actually comes into the picture. So I have like 1 to 11. So it would be, for binary search, it would be right minus left by 2 plus left, right? That's the formula because of covering that index 0 scenario, right? So here 1 to 11 is 12, 12 to 6, right? 6. So my medium will be 6. So I will divide 6 with all. So I will get an answer from here, right? Right? Now I have already got an answer when I divided it with 6. Okay, so now I'll try to move to the left side because anyway higher I have seen, right? So I'll move towards the left side. So this is what is happening, right? So you have the 1 to the max, right? Max pile, right? You move from left to right until and unless they coincide. You find the median. Then from that medium you divide each and you increment the hour. If the hour that is calculated is less than equal to, then you want to check the left side. So you move the right from here to here. Otherwise you move the left from here to here, right? Once the left and right coincide, you will just return the right. Once left and right boundary coincide, we find the target value. This is the minimum workable eating speed. This becomes the minimum workable eating speed, right? So that's how this solution works. The trick here was that how do we know binary search will work? Either the input space should be sorted, or when you do a brute force approach, right? Because that's why the brute force approach here is important. You will see a monotonic behavior in the answer space. If the answer space shows a monotonic behavior, that is a clear sign of using a binary search. That is a clear sign of using a binary search. So that was a tip, that was the trick, that was the observation here. That's all for today. I'll see you in the next question. Thank you. Bye bye.